Wenjing is talking, and she's finishing her PhD. And we thought this was going to be an easy PhD. I don't know. Students shouldn't work with me because it always ends up. And so we had access to this deep borehole in Alberta. That very interesting story, but I don't have time to tell it here. We can talk about it later if you want, why it exists. And we thought, okay, just analyze the breakouts, we'll be done, but it turned out to be much more complex. And she had to develop new software and means of analyzing borehole breakout data in anisotropic materials. And so with that, there's the laser and here's the advance. I'm going to let her go. She talks pretty fast.
Maybe that's not work. Oh yeah, a little bit.
There you go.
Okay. Yeah, hello everyone. I'm Wenjing, and thanks Doc for the introduction. My talk today is the complexity of stress characterization, stress heterogeneity versus log anisotropy. For today's talk, I will start about kind of how we normally do the stress characterization and its underlying assumptions of that. And then I will present my two studies trying to question these assumptions. And then finally, I will conclude. When we talk about the stress characterization, we normally simplify it into two principal stresses. The first, which is vertical stress, which is caused by the gravitational loading, and the next two, which is two horizontal stresses, we call the maximum horizontal stress and the minimum horizontal stress. And the reason why we want to know the cause of stress is because technically for any kind of subsurface applications, it's very, for example, for oil and gas extractions or the hydrocarbon and geothermal energy exploration, we will all want to ensure the wellbore stability. And also, for example, if we want to inject something into the subsurface, we want to ensure we do not kind of induce any seismicities. And also, we want to design and displacement of the hydroflux. Therefore, studying the crustal stress is very important. And how researchers normally do stress calculation is through the drill-induced wellbore failures. When we drill a wellbore, which is represented by the circle here, and when we drill a wellbore, and it will redistribute the stress around the subsurface. So the stress will be more concentrated around the 1 and 3 direction, and it will be divergent at the 2 and 4 direction. And if we kind of show the stress quantitatively, we could see that if we apply the far-field stress at SH, but the stress experienced as top and bottom direction is actually experienced 3 times SH. It means that we are experiencing more stress there. In contrast, at the left and the right direction, we could see that even though we apply the compressive stress, but the stress experienced in that left and right location is actually tensile stress. So after we know these stress patterns, we can do the fault analysis, do the stable analysis to know where the wellbore fails. If we assume that rock is the stress is astopic, then we know that where we have the highest stress corresponding to where the rock will break out first. So there has a one-to-one correspondence conventional analysis, and also if we have in contrast, if we have kind of these failure patterns observed in the field, we can do the inverse problem trying to infer for the stress state if we can observe the breakouts and also the breakout azimuth and also the breakout width. All these one-to-one correspondence seems very kind of straightforward, but I want to draw attention to the underlying assumptions of this causal equation that we use widely. The first, which is the anisotropy assumption, and another one, which is the linear elastic assumption. As for the anisotropy assumption, we know that it may be not true because for the sedimentary rocks, we know, for example, for the shell, it's kind of like have the layer structures, so it will affect our interpretation. And also for the metamorphic rocks, it has the foliations and lineations. So all these will complicate our stress interpretations. And so in these two studies, first I will present a program I developed trying to model how the wellbore will fail if we are in the anisotropic rock formations. And the second study, which is I will show you a real case study in the Canadian Craton to see how the rock anisotropy affect our interpretations. And next, for the linear elastic, we know that it's kind of the Hooke's law. It's a simplified Hooke's law. We think that the stress and strain had a linear relationship, but actually it's also not. In the lab, we see that it's not true. So in these studies, we want to know how to characterize the elastic nonlinearity. But because of the time limitations, I will only talk briefly talk about these two studies here. So let's delve deeper into the programs that try to see how the wellbore will feel in the rock anisotropy conditions. As I mentioned before, normally when we do the crustal stress analysis, we think it's a 2D plane strain problem, and also the rock has elastic and strength anisotropy. But recently, due to the kind of like peculiarities of the inclined wells and also the horizontal wells, the outer plane stresses will contribute to the stress concentrations. So we need to know the stress in the 3D, and also for, as I mentioned before, for the shells and also for the foliated rocks, we will have elastic anisotropy. So we also need to understand the stress in the anisotropy formations. And lastly, in addition to the elastic anisotropy, we also have the rock will also experiencing the strength anisotropy if we have the weak planes. So for example, the horizontal lines here, which is the weak planes, and if the normal of the weak planes and the applied stress is oriented at the 0 or 90 degrees, then the rock, which is strong, it's very strong. But if the weak planes and the stress is particularly oriented, then it will fail in the weak planes, so it will reduce the rock strength. So in order to account for all these scenarios, so we propose a generalized problem that can take any 3x3 in situ stress tensors. Also, it can take any symmetry of the rock stiffening matrix, and also we incorporate the weak plane, trying to model how the effect of the weak planes. So now let's see a hypothetical case study from these models. We could see that so in this hypothetical case study, I put a vertical well in the subsurface, and also I apply the maximum horizontal stress along the east and west direction. And I incorporate the weak planes, and the weak plane strength is lower than the matrix stress. We could see that if the weak planes is horizontal, then we do not see any failures in either rock matrix and the weak planes. However, then I want to study how the orientations of the weak planes will change my breakout failures. So I fixed the deep direction at 60 degrees. Sorry, let me bring it out. Laser pointer. So I fixed the deep direction at deep angle at 60 degrees. Then I changed the strike from the 0 degrees to 45 degrees and to 90 degrees, and to see how the wellbore feels. And here, which is the results, the circle here, which I mentioned before, it's a wellbore surface, and we are looking down around the wellbore, and we could see that for all these 3 cases, the wellbore all fails in the weak planes, and there's no failure in the matrix. And also, we could see that the wellbore failures is actually also rotates when I change the strike azimuth. And if we only focus our attention to the first rows here, we could see that if this is what we just assume this is what we find in the field, then here, which is a breakout, which is happening at 90 degrees, then based on the conventional analysis, we will do a simple interpretation that here, which is our interpreted maximum horizontal stress, because the conventional analysis says that the breakout happens perpendicular to my interpreted maximum horizontal stress. But we could immediately know that it's not true, because here, which is my applied maximum horizontal stress that I applied at the beginning. So it's very dangerous to interpret the failure locations as the minimum horizontal stress azimuth if the rock anisotropy exists. So when we have anisotropic rocks, I think it's very kind of important to take the stress anisotropy into consideration, because in this case is now where the weak plane fails is actually a combination of the strength and the stress. Now, after the hypothetical case study, I want to show kind of like a real case study to show how in the field, when we do the interpretation, how rock anisotropy will affect my stress interpretation. We have a well located here, and it's in Alberta. And this well is a well opportunity, as Doug mentioned. It has around 500 meters in the sediments, but it's have kind of like around 1800 meters in the basement. So it's very important. Well, maybe can tell us what's happening into Precambrian basement. And for the stress in this region, for the circles with through going lines here, which is the previous stress indicators from this region, we could see a very apparent northeast and southwest compressions, and it's also very kind of like relatively consistent with the pretectonic motion. But I want to mention that all these stress indicators are very limited to the Phanerozoic sediments because the economic interest of the sediment layers, and there is very kind of like low kind of stress indicator in the Precambrian basement. And the reason why we want to study the Precambrian basement, the stress in the Precambrian basement is because recently with through-going CCS and geothermal explorations, we want to know what's the stress state in the Precambrian basement and whether it's still coupled with overlying sediments. And there's many cases that even though we are injecting the CO2 into the lowest layer of the sandstone layers, but we can observe the seismicity actually propagate to the cratons. Therefore, we need to know the stress in the craton. And after analyze the caliper logs and also the image logs here, the figures here show the breakout azimuth as a function of the depth. The reason why I kind of like deliberately separated into the 3 depth columns because we could see that with each depth sections, the breakout is actually rotated at different depths. For example, it changes from 100 degrees at the first depth section and then changes to 173 at the second depth section and change to 145 degrees. So we indeed have the heterogeneous breakout azimuth, meaning that at the first kind of like at each depth sections, the breakout is relatively consistent, but it changes from different depth sections, which is pretty uncommon because normally we think that for the breakout azimuth, it may kind of like very consistent along the depths. It has no depth variations, but actually kind of in our cases, it's not true. So when I get these kind of like breakouts, I kind of like, should I follow the normal kind of like assumptions, kind of normal analysis, just the rotated breakout azimuth, meaning that I have a rotated maximum horizontal stress, and then in turn meaning that I have a heterogeneous stress around the depths, or is it true, or is the isotropic assumption violated? Luckily, we have access to a few cores from this wellbore, and we could see that the rocks is heavily foliated. And so it may be an indicator that the rock is actually not isotropic. So we proposed a theory that the breakout we observed is actually foliation controlled. The cylinder here just represent a wellbore, and the orange planes represent a foliation plane. So if the foliation breaks, we think that it will more heavily kind of like breaks in these red regions here. So if we follow the scissors to cut this cylinder open, then a plane in 3D, which is a sinusoid in 2D. So we could see that where the red location occurs is actually occurred at a deep direction, and it's not kind of like correlate with the stress direction as commonly assumption assumes. And also if we see the shape of these kind of like red regions, it's kind of like have a crescent moon shape, and a pair of them has a height offset. And it's actually what we observed from the image logs. We could see that clearly see that the breakout we have in these rocks here is not kind of like a vertical rectangular patches, but it's actually have a crescent moon shape, and a pair of them have the height offset. So due to this kind of like series, we also want to see the correlations between the foliations and the breakout. For these figures, the foliation deep direction shows by the gray, and also the red the darker trend, which is the slow shear azimuth, and the magenta color here shows the breakout azimuth. So for the first 2 depth sections, we could see that the foliation deep direction and the breakout correlate pretty well. So it may be another evidence showing us that the breakout observed here is foliation controlled. And then here, which is the result for the lowest depth section, we could see that for these steps is actually we have offset between the breakout and also foliation. So meaning that in the lowest depth section, it may indicate it will still fill in the rock matrix. And the reason for this difference is because if we go back, we could see that at the first depth sections, the rock is very heavily foliated, but at the bottom, the rock is kind of like less foliated. So it also may explain what happens here. And then after we know that the rock is actually kind of like maybe isotropic, so we cannot do the conventional analysis anymore, because conventional analysis just have a one-to-one correspondence, meaning that if we have the higher stress, meaning that it's a location where we have the breakout occurs. But it's actually not true if we have the strength isotropy. And if we have the strength isotropy, then meaning our breakout azimuth is actually not correlate our minimum stress azimuth. So for example, even though have experienced very large stress here, but if my rock is much more weaker around these directions, then my wellbore could have a failure along this direction. Or in contrast, if my rock is much more weaker around these directions, then my wellbore will also fail in this like these patterns. So due to the breakdown of the one-to-one correspondence, I need to propose a new field stress modeling inversion scheme, trying to invert for the stress based on my observations. So for the programs I did, I have no parameters. I input the transverse isotropic elastic matrix into the program, and it's what we measured in the lab. And also I have the formation directions from image logs. And also for the rock stress matrix, I just can't take numbers from literature, and also for the vertical magnitude, I just do the integration of the density rocks. But for the maximum horizontal stress azimuth, I have two assumptions. The first assumption, which is based on the conventional kind of like Cauchy's analysis, just assume that the maximum horizontal stress direction, which is perpendicular to the breakout. And the second assumption, which is I assume that the maximum horizontal stress direction is actually coupled with the overlying sediments. So it's still kind of like have 50 degrees. Then for the boundary parameters, kind of like I do not know, but I given them a bound to pick randomly from this bound. And this is my desired outcomes, which is the stress magnitude. Then trying to incorporate the stress entropy, I take two failure criteria, one for the intercalary matrix and one for the weak planes. And then I just do the Monte Carlo simulations using the programs that I mentioned before, trying to model the wellbore breakouts. And then if the model breakout is same as what I observed, then I will retrieve my desired outcomes. And now I will just lastly show the stress inversion that I did. Remember that we have 3 depth sections. So here I will first show the depth result for the depth section 1, where we have breakout azimuth around 100 degrees. So I have 2 hypotheses. The first hypothesis, which is kind of like Cauchy's hypothesis. So my alpha edge is at 10 degrees, which is perpendicular to the breakout. And my rock the rock strength is isotropic. So the breakout azimuth rotation we observed is actually stress heterogeneous, which is the depth variations of alpha h. And the second hypothesis, which is the weak Biot hypothesis. And in this hypothesis, we take the rock anisotropy into consideration. It meaning that the breakout azimuth rotations we observed is actually controlled by the fluctuations. And also we assume that stress is coupled with overlying sediments, so we have a consistent alpha h. And here the result shows the stress, feasible stress, we inverted the x and y axis, which is the minimum and maximum horizontal stress magnitude, and the blue and the red lines, which is the conventional Barton's equation, and the green patches, meaning the stress field from the Cauchy's equation, and the rainbow color here, which is from the weak Biot cases. We could see that for the Cauchy's case, it's actually the same colors. The color, sorry, I need to mention the color means the probability of that point of the stress take that point. And we could see that for the Cauchy's case, it's very less sensitive. It's actually giving us equal probabilities in anywhere, so it's not have no preference. However, for the weak Biot case, after we taken the weak plane into consideration, we could see that the stress is actually clustered with the highest probabilities. It means that the stress is more probable in these red regions. And also we could see that the stress is overestimated into the Cauchy's case, giving us large maximum horizontal stress. So because of that, we will also get the different faulting regimes. For the Cauchy to give us a stress slip faulting regime, but for the weak Biot case, it will give us a normal faulting regime. And the reason for the interpretation difference is because we take the weak planes into consideration. So if we take this white marker denoted by here and to model how the wellbore feels, we could indeed see that the wellbore is actually feels in the weak planes, not in the conventional color, not feel in the log matrix by the blue color here. So after I do kind of like the same analysis for all 3 depth sections, I want also to do the stability analysis to see kind of like whether it's stable or not. And the more circles here, the blue and the magenta color here, which is represent for the weak BO case and the cautious case, and the solid red and dashed lines, meaning the failure lines for the matrix and the weak planes. We could see that all these all these small circles are far away from our failure equilibrium, meaning that the craton is very stable. It's not kind of like surprising because we know that the craton is stable and we do not see any seismicity there. But I want to mention something about kind of like whether related to the injection pressures, because normally kind of intuitively we think that maybe from the weaker BO case we have the lower stress states inferred, but it does not necessarily mean that we are more stable, because intuitively we think that if we are experiencing less, then meaning we are more stable, but actually it's not true. From the depth at 2000 meters, we could see that the more circles of the weak BO case is actually close to the failure lines, meaning that it will have the increased risk of slip. And the application of that, which is if we want to determine injection pressures of kind of like wastewater disposal, for example, if we want to inject something, we may need to be more conservative into the to take the stress entropy into consideration. So it may reduce the seismicities, for example. Yeah, that's all I want to talk about today. The first study talks about the program I developed is very general, so it can be applied in many applications. It can generalize the stress tensors, elastic entropy, and stress entropy, and also stress characterization could be complicated by the log entropy. And also I presented a few studies that the breakout azimuths will actually rotate with different depths. So, but it does not necessarily mean that we have a stress heterogeneity from the conventional analysis, but it may be the complexities from the weak plane controlled breakouts. And also the stress in the craton could be coupled with the overlying sediment. So it's maybe still be northeast and southwest, and it's rather stable. But the stress field inverted from the weak BO case, it may indicate we have a lower stress state, but it does not necessarily mean that we have a lower risk of slip, but it may be close to the failure envelopes. So weak planes should be considered when we want to ensure the stability of the wells or the subsurface. Yeah, that's all I want to talk about today. And the potentials were all coming from kind of like these publications I did, and here's other references. And yeah, I'm happy to take any questions if you have any. Yeah. Yeah, it's fast.
So how do I get the end of something? Do I need to have a core, or do I have a way to estimate?